Hello everyone. In this lecture we are learning about Booth's algorithm for multiplication of sign magnitude numbers. The algorithm says that in the beginning we first of all initialize AC Qn plus 1 and SC, and the two numbers are BR and QR, where B register stores the multiplicand and the Q register stores the multiplier. Depending upon the value of Qn, which is the last digit of QR, so depending upon the value of Qn and Qn plus 1, which is initialized to 0, if they are 0, 0 and 1, 1, we simply perform arithmetic shift right and decrement the sequence counter. If the value of Qn and Qn plus 1 is 0, 1, we add BR to the accumulator, and if it is 1, 0, we add 2's complement of BR to the accumulator and perform this until the sequence counter SC is equal to 0. Otherwise, we proceed the same task again and again. Let us see this with an example. Here the two numbers are 35 and 3. So BR is 35 and QR is 3. First of all, we take the binary code of BR and add the sign bit. Here 0 is the sign bit. So the total number of bits for representing BR is 7. Another number is 3. So the code of 3 is 011 if we use the sign bit. But we have to make the number of bits in both the multiplicand and the multiplier equal. So here we add extra zeros to make the number of bits equal. And so whenever we represent number, what is important is we have to include the sign bit in both the numbers. Now, since the number of bits is 7, so in accumulator, we initialize it with 7 zeros. We initialize QR with whatever the QR code, and this is this code for QR. Qn plus 1, as in the algorithm, it is always initialized to 0, and sequence counter SC is equal to n, which shows the number of bits of both the multiplicand and the multiplier. Because the greater number is 7, and we convert both BR and QR into same number of bits, which also includes sign bits. This is equal to 7. Now, this Qn, this is Q0 and Qn, this is Qn and this is Qn plus 1. So what is Qn? Qn is the last digit of QR. In Qn plus 1, we have already initialized 0. So as per algorithm, if Qn and Qn plus 1 are 1 or 0, then what do? We add 2's complement of BR as per the algorithm. So what we perform here it is AC, and what is BR? BR is this number. So we add that B and BR complement plus 1. So BR complement 1 is this number. So we add this complement to the accumulator and we get the result. After adding the 2's complement, we perform arithmetic shift right. So when we perform arithmetic shift right, we just repeat this first number because it shows the sign bit, and then shift right. So this one goes here and this one goes here, and we decrement the sequence count. Once again, we check the value of Qn and Qn plus 1. And here once again it is 1 and 1. We once again perform the arithmetic shift right of AC and QR. This one is repeated once again. This 0 goes here and this one goes here, and we decrement the count. Once again, we check the value of Qn and Qn plus 1. So this time it is 0 and 1. This is 0 and this is 1. So once again, what we do when we perhaps 0 and 1, then as according to the algorithm, we proceed to this path and we add BR to the AC. So how much is BR? BR is this number 0, 1, 0, 0, 0, 1. So we add this number, we get a carry, and in multiplication, we discard carry. After performing addition, we once again perform arithmetic shift right. This 1 0 is repeated, and this 0 goes here, and this 0 is shifted here, and it decremented the sequence counter. This time Q0 and Qn and Qn plus 1 are 0 and 0. This number is 0 and this number is 0. Since both are 0, we simply perform arithmetic shift right. So 1 0 is repeated, this one is here and this 0 is here, and we decrement the sequence counter. Once again, the value of sequence counter is 0 0. So once again, arithmetic shift right is performed. 1 0 is repeated, this 0 is moved here and this 0 is removed here, and the sequence counter is decremented. Once again, the value of Qn and Qn plus 1 are 0 and 0. So once again, we perform the arithmetic shift right. 1 0 is repeated, this 1 is shifted to this side, and this 0 is shifted to this side. Sequence counter is decremented, and its value is 1. Once again, the two Qn and Qn plus 1 are 0 and 0. So once again, we perform the arithmetic shift right. Here we get all zeros and this one is shifted here, this 0 is shifted here. So now the sequence counter has become 0. Here the MSB is 0. That means the number is positive. So we simply take AC and QR. So this is AC and this number is QR and this comes to be 105 because here MSB was 0. So our answer is positive. So multiplication of 35 and 3 is 105. Let us take one more example where one number is negative and the other is positive. So once again, we perform the same thing here because the number is -3. So first of all, we find the binary representation of +3. Then we make all the number of digits equal to 7. Once the number of digits in +3 is made 7, we take 2's complement to represent -3. So here the procedure is the same, but only difference is that we have taken this code as -3. So QR is so many ones and 0, 1, where this one represents the sign. So depending upon the value of Qn and Qn plus 1, if it is 1 and 0, we add 2's complement. If it is 0 and 1, we add the BR simply and not its 2's complement. And if it is, once again, if we can see if they are 1, 1 or 0, 0, we do not perform addition of either BR or 2's complement. We simply perform arithmetic shift right. So this is how we proceed further, and you can see the various arithmetic shift right as were performed previously. And this is how we get the result. Here we get the result in MSB, we get 1. So that means the number is negative. And if the number is negative, once again, we take 2's complement of AC and QR. So this is AC and this is QR. AC, this is AC and this is QR. We take 2's complement. So when after taking 2's complement, we get this number. So this number corresponds to 105, but because we have received here 1, that means the output is negative. So the output here, the sign bit of the output is 1. Thanks for watching.